In the previous video, we saw what were the drawbacks of the Rutherford's model. Now, his student, Niels Bohr, he came across another theory of how the atoms are, how the particles within the atoms are arranged. In other words, he gave the structure of the atom. Okay, so what did he do was, see, Rutherford's model, the stability of the atom, there was no conclusion in it, correct? There was no conclusion, there was no mathematical form for the spectrum of the line, spectrum, atomic spectrum and everything. Niels Bohr, he gave a particular theory which could explain these things. Okay, now, so what he did was, before he actually gave the atomic model, couple of postulates which are very important called as Bohr's postulates, he assumed these postulates, okay, and then he gave these postulates. So the very first thing is, see, in a hydrogen atom, the negatively charged electron revolves in a circular orbit around a heavy positively charged nucleus. Okay, the centripetal force required by the electron is provided by the attractive force exerted by the nucleus on it. Now, this is the first postulate of Bohr. See, one important thing is, whatever the postulates Bohr postulate or postulates Bohr has given, we need to recreate the same thing. That particular thing cannot be changed. It has to be the same. So, again, I'll just tell you what it is. The first postulate of Bohr: in a hydrogen atom, the negatively charged electron revolves in a circular orbit around the heavy positively charged nucleus. The centripetal force required by the electron is provided by the attractive force exerted by the nucleus on it. This is the first postulate what Bohr gave. Okay, which is very simple. You have an electron, you have a nucleus. The centripetal force is given by the electrostatic force of attraction between them. This is the first postulate. The second postulate, here this particular postulate is very important. All right. So what we have is, the electron can revolve around the nucleus only in those circular orbits in which the angular momentum of an electron is an integral multiple of h by 2 pi, where h is Planck's constant. This is the second one. Now, again, I'll repeat this. The electron can revolve around the nucleus only in those circular orbits in which the angular momentum of an electron is an integral multiple of h by 2 pi. Now, this particular postulate is very, very important for further derivations and further conclusions. So what we have that an electron is revolving around the nucleus in a circular orbit. Now, these orbits, see, whenever the electron is revolved in that particular orbit, no energy is radiated by those electrons. That means they are stationary. You can say these orbits are called as non-radiating or stationary orbits. Okay, these orbits. Clear? And then each stationary orbit is associated with a definite amount of energy. Okay, so they say that if it is in the second orbit, it has a definite energy. First orbit, it has a definite energy. Clear? Now, this was one of the things, or you can say this was one of the postulates which saved the Bohr's model compared to Rutherford model. Rutherford did not assume it to be non-radiating or stationary, isn't it? So this is the second one. Now, mathematically, we can do this one. That is, suppose if m is the mass and v is the velocity of the electron, and then it is moving in a particular orbit, right? Say the orbit is r, the radius is r. Okay, then we get mvr is equal to n into h by 2 pi. This is the mathematical form of second postulate of Bohr. That is mvr is equal to nh by 2 pi, where n is an integer. Alright. The third postulate, what we have is the energy is radiated when an electron jumps from higher to lower energy orbit, and the energy is absorbed when it jumps from lower to higher energy orbit. This is the third postulate. Okay, that is, energy is radiated when the electron jumps from higher to lower orbit, and the energy is absorbed when it jumps from lower to higher energy orbit. Alright, this is the third postulate of Bohr. So here it's very simple. Suppose let's say EI is the initial energy, okay, and EF is the final energy. Then see, whenever an energy is absorbed or whenever the energy is given out, as in it is emitted, the energy has a particular frequency. Say the frequency is nu. Then the energy, or you can say the radiation emitted, is given by h nu is equal to EI minus EF. This is the mathematical form of the third postulate. So, to wind up, what we have is the first postulate of Bohr. It tells us that whenever we have a hydrogen atom, the electrostatic force between the nucleus and the electron, that accounts to the centripetal force between them. The second postulate, this particular postulate is also called as Bohr's quantization condition. Okay, this is given by whenever we have an electron in a stationary orbit, then we have mvr is equal to nh by 2 pi. So here n is 1, 2, 3, 4, or you can also call it as principal quantum number. Okay, mvr is equal to nh by 2 pi. And the third postulate is about the energy. That is, an electron jumps from lower to higher when it absorbs, and from higher to lower when it is emitting. And that energy is given by the difference, or you can say the energy of the radiation is given by the difference in the energies of the orbits. That is, h nu is equal to EI minus EF. Now, taking these postulates into consideration, in the coming videos, we'll see how mathematically we can derive the Bohr's postulates and the Bohr's atomic model. That is, we can talk about what is the energy, what is the radius, what is the velocity, all the parameters relating to the atomic model we can discuss in the further videos.